We're going to look at section 12.2 today, which is our first introduction to surface area. And we're going to kind of do it in the context. I'd like the sum of the areas of the faces. One method is to find a net, which is simply a 2D drawing of a 3D figure. And it works fine and dandy. Drawing nets takes some pretty, maybe not developed or powerful, but it's going to take some visual skills here in order to figure out what's going on. So in the case of my rectangular prism here, I'm going to call the this guy here the base. So if I think of a two-dimensional representation, I'm going to leave this rectangle that's on the back stationary. It's got a length of 7 and 5. I'm going to fold down one of the bases. I'm going to fold down the bottom. I'm going to fold up the top. And then I have to fold out the sides. So I have like this. I have this face that's here, on looking at it on the right. I'm going to fold this side face out, which has a length of 6. I'm going to fold its partner out, which also has a length of 6. And then I have the front face that gets folded twice, which has a length of 5. This would be an example of a net for this rectangular prism. And if you want to find the surface area, then from this net, now you could just calculate all the areas of the rectangles and sum them together. Would be one way to do it. Note this net is not drawn to scale. It's not even close to drawing, and you would not be able to cut this out and actually get this guy, but it's more of a factor of mind drawing. So again, you could add up all the individual areas. There's 6 of them. I think a more efficient way to do things is the following. Note that you have two congruent polygons up here. No, there are 2 rectangles. I'm going to represent their area by a capital letter B. Note that then we can look at this big rectangle. We're going to try to calculate the area of this big rectangle in one fell swoop. What does this yellow highlighter length correspond to in our original drawing? 7. So where's the 7 in our original drawing? It's the distance between the 2 bases, which we'll call the height. The distance between the 2 bases. We'd also like to know what that length is. What does that red dotted line correspond to in our original drawing? 5, 6, 5, 6. So this is the perimeter of the base. So the area of this big rectangle then better be the perimeter of the base times the height, which is the distance between them. So a formula, the formula we're going to use for calculating the area of a prism whether it be a rectangular prism, whether it be a triangular prism, which we'll see an example of in just a second. We're going to find the surface area is twice the area of the base plus the perimeter of the base times the height. Note that I'm going to use capital letters for areas when I write them in a formula. So capital B here is the area of one base. Perimeter is the perimeter of the base. P is the perimeter of the base. And H is the distance between the bases, also known as the height. I don't want to. I want you to memorize or know that H is really this quantity, distance between the bases. And the reason I say this is because if you attach the word height, most people think of height as like up and down, as vertical. But the height doesn't have to be vertical. There's nothing that says it has to be. In fact, in our second example here, we're going to find a height that's not vertical. The height is the distance between the two bases. So you have to identify what the bases are and then find its distance. The trap here is, unfortunately, I picked a rectangular prism to start with. The issue with picking one of these guys is that any of these 6 faces could have been a base of the rectangular prism. Does anyone know why? Because every face has a congruent opposite pair. And each of those is always connected by rectangles. All the things are rectangles. In our next example, there'll be a very distinct face. I'd like to, I don't have numbers put in, so let's fill some in. I'd like this piece to be 3, this piece to be 4, this piece to be 5, and we'll call this piece 2. And how about we even go meters? Be a big thing. Before you can jump into a formula, you need to know what the base is. So where is the base on this figure? Okay, why is it the triangle and not, say, this rectangle? 2 congruent triangles across each other. What would you call this prism? We're going to name prisms by what the shape of their base is. So if the base in this case is a triangle, then we'll call this a triangular prism. So it can really help. To just identify what the prism's name is, and then that should point us in the direction of how to continue the problem. So in this case, this triangular prism, we know that the base here, or one of the bases, has to be a triangle. So everything we do in this formula is going to be based off knowing that this base is a formula. Is a triangle. Surface area has got to be twice the area of the base plus the perimeter times the distance between the bases. So if we can calculate those things, what's the area of a base in this case? What is the base? We said it's a triangle. So what's the area of this right triangle? 6. Half times 4 times 3. What's the perimeter of the base? 3 plus 4 plus 5. What's the height? What's the distance between the two bases? 2 meters. So the surface area, once we've calculated these things, has to be twice times 6 plus 12 times just 12 plus 24 or 36 square meters. Okay. Note that we're finding an area, so your units better be area units. In this case, square meters. Questions so far? Sorry, not cone. A cylinder is a circular prism. It's a prism that's got tops instead of polygons. They're two circles, but they're congruent circles, and they're connected. And they're connected by this continuous, continuous strip. These are however, the same formula applies to these shapes. So in general, the surface area of any prism should be twice the base plus the perimeter times the distance between them. For cones, however, we have specific polygons, specific shapes, specifically circles, which are not polygons, but specific circles. And we know we know a lot about the areas of circles and the perimeters, or another word for that, circumference of the circle. So this formula, if you want to memorize it or as adapted specifically to cylinders, you're welcome to. Twice the area of a circle is pi r squared. The perimeter of a circle is its circumference, which is 2 pi r, and the height is still the height. Would be a formula specific to cylinders if you wanted to know that. You could I simply memorize this and then just apply it to circles, but you can do whatever you want, I guess. If you wanted to get another formula in terms of just the radius, it's fine. Let's just as a quick exercise here, let's add some numbers in here and come up with something. How about, let's say the radius of this circle is, how about 3 inches, and we'll say the height is, how about 7 inches. Please calculate the surface area of this cylinder. So our surface area is about 188 square inches. Okay. So we've seen rectangular prisms. We saw triangular prisms. Circular prisms, also known as cylinders. Let's look at our last one here. Let's look at a prism with regular faces. In this case, I have a regular hexagon as its face. And I ask you to find the surface area. So let's see, surface area is twice the area of the base plus the perimeter of the base times the height. Which means we're going to have to calculate, if you knew what the area of the base was, you knew what the perimeter was, you knew what the height of this prism was, then we just plug in and go. I claim that 2 of these things you can basically read off, and the third we're going to have to do a little bit of possibly extensive work. Which 2 of these things are the easy ones to calculate?
The perimeter and the height.
Perimeter and the height. Height being the distance between the 2 hexagons, which is 8 feet. It's a regular hexagon, and if any one side is 4, then the perimeter is 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. 4 times 6 is 24. So now the key is got to find what the base is. So the area of the base is the area of this regular hexagon. And if you recall back from last chapter, the area of my base in this case is going to be half of the apothem times the side length times the number of sides. Or maybe more convenient, since we already calculated the perimeter. Side length times number of sides is just the perimeter. We already got that. So we have to figure out what an apothem is for one of these guys. There's an apothem. Each of those is 4. So what do we say? We have to, our strategy was to create triangles out of this. The central angle, this central angle here should be 360 over 6, which is 60. half of it is 30. So I'm really working with this 30, 60, 90 triangle, trying to find what the apothem is, and I know that the side length, the whole thing is 4, so if I bisect it, this piece is 2. So you could use sine, cosine, or tangent if you wanted. Hopefully you remember your special right triangle rules, because a 30, 60, 90 right triangle says that the long leg is just the short leg times root 3. So the apothem in this case better be root 3. So in the area of a base here, it's half of 2 roots of 3 times 24, which is 24 roots of 3, which is, what is it, about 41 or so? Half times the apothem times the perimeter, or side times number of sides, perimeter. So 24 roots of 3 is what, 41 point what? Square feet. So now you've got this stuff, the surface area shouldn't be so bad. Surface area should then be twice of 41.57 plus 24 times 8, which comes out to be what, about 171, I think? 175 or so. What was it? Is it 275?
Oh, yeah.
80 and, well, yeah, 2. Point what? Ends up being approximately 275 for square feet.